right, so we're back to stoichiometry. I know, everyone's favorite. We haven't done this in a little while, so I want to remind you of what we did way back in Unit 2. We did two operations back there. One, we looked at something within a chemical. For example, maybe we looked to see how many moles of nitrogen are in dinitrogen monoxide or something like that. And in that case, we generally started with grams. In this case, we'll say grams of N2O, because that's what I picked out there, N2O. And then we use the molar mass to get to moles of N2O. Then we used a molar ratio. And in this case, we're interested in how many nitrogen grams there are, for example. And so we use the molar mass to get from 1 mole of N2O to 2 moles of nitrogen. Now, in this case, it's just the atom nitrogen, not the elemental molecule. And then we would have used grams of nitrogen for every mole of nitrogen. And so we did that within a chemical compound. We also did this for a balanced chemical reaction where, for example, let's assume we've got, we'll come back to, we'll actually be doing this problem in a little while, but we've got, say, oxygen converting to ozone, and in that case we would start with usually grams of O2, then we convert that to moles of O2 using the molar mass. Then we use, remember, you've always got to get to the mole of the chemical. That's very important. And so in this case, we would be going to, using our mole ratio, 2 moles of O3 for every 3 moles of O2. And then we would convert to grams by using the molar mass again. So here's this mole business, okay, back in our pressure, volume, temperature, etc. type of work. Okay, again, that is the heart. This is the heart of that ratio, okay? And so we're going to be, oh, and I forgot. We also had another thing that we needed to do, and the reason I want to bring that up is because Avogadro's number is going to come back up now. And in this case, maybe we started with the number of particles of A, for example. That's what we knew. And then we would have used 1 mole of particles over 6.022 times 10 to the 23rd. Remember that lovely number, Avogadro's number. 1 mole of A over that many particles. And then maybe we'd have to do a mole conversion. Okay, so maybe we have 2 moles of B over a mole of A. And then we could have also found out how many particles of B we had for every, oops, that should be, let me redo that. That should be 6.022. Avogadro's number won't fit, so I'll say Avogadro's number of particles for every mole. All right, so we've done all these before. Now we have one more little twist here. Now we're going to take information we know about gases using the ideal gas law. And we're going to convert that to moles of whatever we're talking about. Okay, what we know, this is our known. And we're going to convert that using the mole ratio again to the unknown. Okay, Now, we can give you information about the known to find the moles of the unknown, or we could ask you how much the volume or the pressure or something is of the unknown. Okay, so this is going to be our scheme. All right, oops, I don't want to extend the page. I want to change the page. This is going to be our scheme in this particular problem. Okay, so I've broken it down into a little bit smaller amount here. And so we are, in this problem, we're going to know information about the pressure, volume, and temperature, so we can find N. That's what we want to find out of our pressure, volume, and temperature information. Then we can use that amount of N for some gas using our molar ratio from the balanced equation, again, to find the moles of B. I could also ask you harder questions, or a further question rather, where I might ask you how many grams of B there are at the end of the reaction, or something like that. So this is still the same kind of scheme, only this time you have to calculate N somehow. So in this case we have propane, C3H8. It's combusted at some temperature and some volume and at some pressure. Okay, and so the question is, how many moles of CO2 can you get? All right, well, we know about this, and we want to know about this. Typically, you'll need to be able to balance an equation, or at least check and make sure you have an equation, and the equation is balanced. It's just good practice. So let's see. In this case, we've got C3H8, where we know the volume is 75 mils. All right. We also know that the pressure is 890 torr, and we know that the temperature is 202 degrees Celsius. Now, we can't use any of these numbers in our ideal gas law, which is how we're going to find N. The pressure volume is equal to nRT. All right, well, because R is 0.0821 liters atmosphere over mole times Kelvin, of course, I can't just go straight to answering the question because none of these have the right units. Okay, but I can convert that. So my temperature is going to be 475. Volume is 0.75 liters. Just in case you've forgotten, that's 1 liter over 1,000 mils. And people turn these around and backwards all the time. So even if you're pretty sure you know what the volume is, double check yourself and make sure you've got it in the right direction. And then you find the number of atmospheres given your torrs. You'll rearrange PV is equal to nRT, okay, to get, now we know everything. We know the pressure, we know the volume, we know R, we know temperature, and so we can calculate N, all right, or the moles of the C3H8, or the propane. But that's only part of the problem because we need to get to moles of CO2. So solving this problem gives me moles of propane. Now, I need to convert using the balanced equation over to the moles of CO2. And so, in this case, I'm beginning with 2.25 times 10 to the negative 3 moles of the the propane. And I look at my balanced reaction. There's 3 moles of CO2 for every implied 1 mole of C3H8. And that tells me when the reaction is finished, I should have 6.75 times 10 to the negative 3 moles of CO2. Okay, so in this problem, we used PV and T info in the ideal gas law. And that gave us N of, in this case, the reactant C3H8. Okay, second, we took the moles that we calculated of C3H8, and using a mole ratio, we converted to moles of CO2. All right, so that's kind of the steps that you need to undertake here. All right, so it's all we're doing is one more thing. Now, I told you a minute ago, I could ask you a little bit more in-depth problem. Like I could say, for example, how many grams of CO2 will form in this reaction? Well, that's just one more step, and you should know how to do that pretty well. This would be 6.75 times 10 to the negative 3 moles of CO2 times, I'm going to use the molar mass, it's 44.01, 44.01 grams of CO2 for every 1 mole of CO2, and therefore I would expect to get in my experiment 0.297 grams of CO2. Okay, so this is an extension. Okay, this is a little extra. Now, I could also ask something like, what is the volume of CO2? All right, so in this case, I wouldn't be going over to the grams. Instead, I would be using this scheme. Let's go up here a little bit, where we know we calculate PV over RT to give us N. And that was the moles of C3H8. Oops, C3H8. Then you can convert to moles of CO2, just like we saw up here. Okay, this part of the equation. But then I could ask you, what's the volume of CO2? Okay, well, if I did that, then you'd have to go back to ideal gas law, and you would use volume is equal to nRT over pressure. Okay, so there's lots of turns and twists that can be taken on, but typically you'll want to use always for these, you're going to use the ideal gas law in some way, and you're also going to be using regular stoichiometry to work these problems. So let's do a couple more. So in this reaction, we have ammonia reacting with oxygen. It forms nitrogen monoxide and some water. Okay, so I gave you the reaction. And there's 35.6 liters of ammonia, and I want to know, and the conditions are STP. Now remember, STP is standard temperature and pressure, where the temperature is 0 degrees Celsius and the pressure is 1 atmosphere. Okay, so I know all the conditions. I know the volume, the temperature, and the amount, so I can figure out what N is. So first I'll start with finding the moles of N, or the moles, in this case, of ammonia. That's what I know about. So the moles of ammonia will be equal to PV divided by RT. Okay, and in this case, that's going to be 1 atmosphere, that's standard, times the 35.6 liters in this question, divided by 0.0821 liters atmosphere over mole times Kelvin. And I know you guys don't want to write it, but write it anyway. And then our temperature is going to be not 0, because we never use Celsius, but 273 Kelvin. And let's see, when you calculate that up, that works out to be equal to 1.59 moles of ammonia that's in this container, 1.59 moles of ammonia. Now, I want to know how many grams of water are in this reaction. Okay, but I'm talking right now about ammonia. Okay, so I've got to use some kind of a mole to mole ratio to get over to the water in this case. Well, I know that for every 4 moles of ammonia, I have 6 moles of water. Okay, so I'm going to say 1.59 mole of ammonia, and then I'm going to use stoichiometry and say 6 moles of H2O for every 4 moles of ammonia. And this works out to be equal to 2.38 moles of water produced when this amount of ammonia is started. So that's what I would expect to get in water. And finally, I'm almost done, but I did ask how many grams of water, not how many moles. The question would probably have how many moles there are as an answer, but you wouldn't be finished though, so you want to be sure and take 2.38 moles of H2O times the grams, 18.02 grams for every mole, and this works out to be equal to 42.9 grams of water. Okay, so all I did was use the ideal gas law, step 1 here, to find N. Then I used stoichiometry to get to the moles of whatever the unknown was. And then, in this case, I finished the question. All right, so in this case, all I had to do was convert to grams. Let's do another one. I've got a reaction of oxygen and forming ozone. I've been told that I have 0.5 moles of oxygen. Okay, so I already know in this scheme where I had to use PV is equal to, or PV divided by RT is equal to N. Well, I don't need to do that in the first step. I already have that. So I also have the conditions, 25 degrees and 1 atmosphere. I want to know what the volume is. I probably should have said in this problem, assuming a complete reaction. So we're going to assume that all of the oxygen is converted to ozone. So my first step here, step 1, since I already am beginning with moles, I'm going to begin with converting mole of O2 to mole of O3. All right, and I'm going to use the molar mass to do that in the, the molar ratio. So step 1 is stoichiometry in this problem. Then I'm going to take the calculated moles of O3 and I'm going to apply them to the ideal gas law to answer this question about the volume of O3. So, for our problem, we have 0.5 moles of oxygen, O2, and notice how that's written, by the way. Oxygen is left for you to decide whether that's a molecule or just an atom. In this case, it's a molecule. 0.5 moles of O2, and in my balanced reaction, I can see I have 2 moles of O3 for every 3 moles of O2. So times 2 moles of O3 for every 3 moles O2 tells me that when I get done with the complete reaction, I'll have 0.33333 or something moles of O3. Now I'm ready to put this. My real question is, what's the volume? My question is, what's the volume? All right, so I can take this N value right here and insert it into, I can take that N value and insert it into PV is equal to nRT. I'll rearrange that because what I want is the volume, and I know everything else. So the volume is equal to nRT divided by the pressure. In this case, that's going to be equal to 0.33 moles of O3 times R, 0.0821 liters atmosphere mole times Kelvin, times my temperature, which was 25, so I'd better be sure and say 298 Kelvin, and divide that by 1 atmosphere, our pressure in this problem, and that works out to be equal to 8.1 liters. Okay, so in this case, instead of starting with the ideal gas law, I ended with the ideal gas law. Now I have one more problem. It's pretty in-depth, but I want to show you how to do this. This is a limiting reagent problem. All right, and in this problem, I'm told all kinds of information. I'm told about all the information about CH4. Okay, I'm told about all the information of CO2. And I'm told about, all the information of oxygen. Okay, and each of these has a different pressure, volume, temperature, etc. These two are mixed together, and our purpose is to figure out how much, in terms of liters, the CO2 is. All right, so this is a relatively complicated problem. And on top of all that, there's not even a balanced equation. So I've got to have a balanced equation to start with, so I know under combustion circumstances that I'm going to have CH4 and oxygen. I just don't know how much oxygen yet. But the rule says for every carbon, I form a CO2. So I have one carbon, so I'll form CO2. And hydrogen forms water, so I'm going to need 2 H2Os. That's going to give me 4 oxygen atoms on this side. And so my coefficient for oxygen is going to be 2. Why do we care? Because we're going to be doing stoichiometry, and we've got to have a balanced equation. Now, before I get started doing anything on this, I want to figure out how many moles of the methane are there and how many moles of the oxygen are there. First thing I'm going to do is decide about my limiting reagent. All right, so I did try to make this not terrible. Okay, so I gave everything to you in the actual, standard things that we're going to be using, except the temperature, because I never want you to forget to convert that to Kelvin. So for CH4, we want these moles. All right, so we're going to put in, and I would recommend a table here, but we don't have enough room for that. Slash there. We don't have enough room for that, so I'm going to go ahead and do this conversion for you so you can just see. But if you were doing this on a piece of paper, you'd want to write down each one's. For CH4, you'd want to know its pressure, volume, temperature. For O2, you'd want to know pressure, volume, temperature, amount, or whatever you know. Okay, so you ought to make a little table to help yourself. Excuse me, but in this case, I'm going to take N for CH4. I should have done N for CH4. That's going to be equal to 1.65 atmospheres. Oh, I'm sorry, I've got that red pen out. 2.80 liters. We're going to divide that by the constant. And the temperature at 298. And we're going to discover that that gives us 0.189 moles of methane. Now that was the methane. Okay, I'm also got to figure out what's going on with the oxygen. I know a volume, I know a temperature, and I know the pressure. So I can find the N of O2 And in that case, that's going to be 1.25 atmospheres times 35 mils. I'm sorry, 35 liters divided by that lovely R constant that I admit I get tired of writing to. And the temperature here is 304 Kelvin. So when I get done, I have 1.753 moles of O2. Now this is a limiting reagent problem. So I have to go to a product, okay? You compare the two reactants to the same product so you can decide what's limiting. Okay, so I'm going to look and see. All I've done so far is figure out how many moles of things, how many moles of reactants we started with. I hate to do that, but here we go. I'll put that back up for you in a minute. So I've got to convert now from our reactants to a product, one product, so I can compare and decide which one gets the least amount, so I can know what my least amount could possibly be. So in our reaction, we see there's 1 mole of methane for every 1 mole of carbon. And so our mole ratio, CH4 times 1 mole of CO2 for every 1 mole of CH4 indicates that we have 0.189 moles of CO2 if this reacts completely with the other thing. Now, for our oxygen, 1.753 moles of O2, I've got to get into the right unit. I have 1 mole of CO2, that's the one I want to know about. And we could just as easily have picked water, but we're interested in this one this time. And this time, remember we have stoichiometry here, so that's for every 2 moles of O2. And so when we get done, we end up with 0.876 moles CO2 if all of the oxygen reacted. Now, this is a limiting reagent problem, and now that I've gone to analyzing this product, okay, I can now decide which one is my limiting reagent. The least amount I can get from this reaction is the most amount I can get is from 0.189 moles of CO2, which makes methane my limiting reactant. Okay, so limiting reactant is equal to the methane, CH4. Am I done? No, of course not. We can't see any of that information anymore, so the question is, what volume of CO2 is produced if the pressure is changed to 2.5 atmospheres and the temperature is 125 degrees Celsius. So we add these two separate gases together, okay, and we figure out how much of volume we would expect. And we can do that using volume is equal to nRT divided by pressure. So again, the ideal gas law. And this time we've got to be sure that we use our limiting reagent to calculate this. So that would be 0.189 moles of CO2 times, I'm just going to write R for the sake of, because I'm tired of writing that right now, times the temperature. So am I happy if you put in 125 degrees Celsius? Is the answer there if you put in 125 degrees Celsius? Yes, but that's not the thing to use. This would be 398 Kelvin. Divide all this by 2.5 atmospheres. And we end up with volume equal to 2.47 liters of CO2. Okay, so I know you haven't done stoichiometry in a while. Try not to let yourself get worried about it, but practice and practice and practice, okay?